You stocked your home STEM lab with Arduino boards, a 3D printer, soldering gear, maybe even a laser cutter. But here's the thing. Before your kid powers up that first circuit or loads filament into the extruder, the space itself can become the biggest hazard in the room. I'm Chloe Miller, and today we're walking through the infrastructure checklist that turns a corner of your home into a legitimate, safe learning lab. Power, ventilation, storage, and what to do when things go sideways. You're listening to the STEM Lab podcast. Quick note before we get started, everything you're about to hear is researched, fact-checked, and written by real people. But the voice you're hearing is AI generated. We're transparent about that because it matters. Anyway, if you've been listening for a while, I really appreciate you being here. And if this is your first episode, welcome. Glad you found us. We drop new episodes every Monday, Wednesday, and Friday, covering the practical side of STEM education at home: safety, gear, project ideas, how to set things up without burning the house down. Now, here's what we've got for you today. If you're still trying to figure out where to set up your STEM space, you might want to check out our guide comparing dedicated STEM rooms versus multi-purpose learning spaces first. But once you've picked your spot, let's talk about what it actually takes to make it safe. Now, let's start with power and electrical safety. Electrical capacity is the hidden constraint in most home STEM labs. You'll notice at the moment you try to run a 3D printer that pulls 200 to 300 watts, a soldering station drawing another 50 to 80 watts, and an oscilloscope, all on the same 15 amp circuit. That's not just inconvenient, it's a fire risk. If you're running FDM 3D printers, laser cutters, or bench power supplies, you want a dedicated 20 amp circuit. That gives you 2400 watts of capacity at 120 volts, with headroom for multiple devices. Standard 15 amp circuits max out at 1800 watts, and you should never exceed 80% continuous load. That's 144 watts. A 3D printer alone can hit 250 watts just warming up the heated bed. We've got more detail on 3D printer power requirements in our station setup checklist if you want to dig deeper. Next, GFCI protection. If your workbench is anywhere near a water source, you need ground fault circuit interrupter outlets. These trip within milliseconds if current starts leaking, which is critical for chemistry experiments, hydroponic setups, any kind of wet lab work. The National Electrical Code already requires GFCI in bathrooms and kitchens, but your STEM space needs it too if you're working with conductive liquids. Here's something people overlook: surge protection rated for data lines, not just power. Cheap power strips might absorb one surge before they're done. Look for surge protectors with joule ratings above 2000 and protection for data lines like Ethernet and USB. When your teenager is running experiments controlled by an Arduino with hours of unsaved sensor data, a lightning strike shouldn't wipe the whole project. You also want individual power switches for each workstation. You need the ability to kill power to the 3D printer zone without shutting down the Raspberry Pi that's running a 48-hour environmental data logger. Switched outlet strips or wall-mounted switches give you zone control and make shutdown protocols a lot easier to enforce. Label your breaker panel. Clearly mark which breakers control your STEM lab circuits. Imagine your child needs to emergency stop a piece of equipment and you're not home. A clearly labeled breaker, something like STEM lab east wall or 3D printer circuit, turns a panicked moment into something manageable. Don't use extension cords as permanent wiring solutions. Extension cords are temporary tools, not infrastructure. If you need power where an outlet isn't, install one. Daisy-chained extension cords hidden under desks are how house fires start, especially when they're buried under flammable materials like cardboard project boxes. Make sure your equipment matches your region's voltage. Most Arduino kits and robotics platforms are globally compatible, 5 volts DC via USB, but some imported lab equipment, older oscilloscopes or specialty tools, might expect 220 to 240 volts. A step-up transformer works, but it's another point of failure. Verify input voltage specs before you buy. And here's a big one: accessible emergency shutoff. Mount a large red emergency stop button within arm's reach of your primary workbench.
Commercial versions run around $15. It should cut power to high-risk equipment, soldering stations, 3D printers, heat guns, with a single palm strike. Train every lab user on where it is. Moving on to ventilation and air quality. 3D printing with PLA smells kind of like maple syrup or corn, pleasant even, but it's still releasing ultrafine particles and volatile organic compounds. Home STEM lab safety goes way beyond just opening a window. You're managing cumulative exposure over months and years. You need active ventilation rated for your room. A bathroom exhaust fan isn't going to cut it. Calculate your room volume, length times width times height in feet, then divide by 60 to figure out the CFM, cubic feet per minute, needed for 4 to 6 air changes per hour. A 10 by 12 room with 8-foot ceilings is 960 cubic feet. You need 64 to 96 CFM minimum. Inline duct fans or dedicated air purifiers with HEPA filters do the work. For soldering and electronics work, get a fume extractor. A simple benchtop fume extractor with activated carbon filters runs around $40 to $120. Position it 6 to 8 inches from the soldering tip, and it'll capture flux smoke before it reaches your teenager's lungs. Lead-free solder still releases irritants. If you're teaching electronics seriously, this isn't optional. Our robotics learning path covers progression into PCB soldering if you want more on that. 3D printing needs separate ventilation. Enclosed 3D printers contain fumes better than open frame models, but you still need exhaust. A flexible dryer vent hose, about $10, ducted to a window, works for occasional printing. For daily use, consider a HEPA air purifier with activated carbon rated for VOCs, placed within 3 feet of the printer. We've got a guide breaking down the emission differences between enclosed and open frame 3D printers for kids. Consider an air quality monitor with VOC and particulate sensors. Devices in the $150 to $200 range give you real-time readings for PM 2.5, VOCs, and carbon dioxide. You'll discover that PLA printing spikes PM 2.5 for 20 to 30 minutes after a print. ABS is worse, and poor ventilation during soldering pushes VOCs into the yellow zone. Data makes invisible hazards visible.
Here's the hard rule. No STEM work in bedrooms without extraordinary ventilation. Kids metabolize chemicals differently than adults. Even materials labeled safe, like PLA, release nanoparticles that settle on bedding, carpets, and stuffed animals. If your only option is a bedroom setup, restrict activities to low-emission work. Coding, robotics assembly, breadboard circuits, and relocate 3D printing, soldering, and chemistry to a garage or basement. If you're using any combustion or gas-powered experiments, install a carbon monoxide detector. This is rare in most home STEM labs, but if you're exploring internal combustion engines, gas-powered rockets, or fire-based chemistry, a CO detector is non-negotiable. Place it at breathing height, not on the ceiling. One more ventilation note. If you're pulling 200 plus CFM out of a room, say multiple fume extractors running at once, you need makeup air. That's a passive vent or a slightly opened window so the room doesn't go negative pressure and start pulling exhaust back through cracks or other vents. Now let's talk about storage and material handling. Poor storage compounds every other safety risk. A toppled shelf can dump a gallon of isopropyl alcohol onto a powered circuit board. Loose filament spools become trip hazards. Chemistry reagents stored at eye level with no labels? That's how accidents happen. Store flammable liquids in metal safety cabinets below waist height. Isopropyl alcohol for cleaning prints, acetone for ABS smoothing, contact cement for craft projects. All of these need ventilated metal cabinets, ideally OSHA compliant. You're looking at around $200 to $400 for a 4-gallon capacity. Plastic bins melt in fires. Glass bottles shatter when dropped. Store below waist height so a fall doesn't rain flammable liquids onto your face. Battery storage matters, especially for LiPo batteries used in RC projects and drones. These are high energy density, which is engineering speak for they burn hot and fast if punctured or overcharged. Store them in LiPo-safe bags or ammo cans, $15 to $30, never fully charged. Storage charge is 3.8 volts per cell. Keep them away from conductive materials.
Shelving needs to be rated for actual load and anchored to wall studs. Wire shelving might say 250 pounds per shelf, but that's evenly distributed, not a 3D printer cantilevered on one corner. Use plywood-backed industrial shelving and anchor L brackets to studs with 3-inch lag bolts. I've seen a $400 3D printer faceplant because someone trusted drywall anchors. Use a clear labeling system with hazard symbols and age restrictions. Label maker or printable stickers with GHS hazard symbols available as free PDFs from OSHA for anything corrosive, toxic, or flammable. Color code by hazard type. Mark age restrictions. Soldering, 12 plus with supervision. Chemistry reagents, adult use only. It's a teaching tool and a safety net.
Store 3D printer filament in airtight containers with desiccant. PLA, PETG, and especially nylon absorb moisture from the air, leading to brittle prints and clogged nozzles. Vacuum-sealed bags or airtight bins with silica gel packets, you can reuse them. Just dry them in the oven at 200 degrees. Keep filament printable for years. Our Filament Types Guide explains hygroscopic behavior in detail. Get small parts organizers with anti-tip bases for resistors, LEDs, fasteners. Imagine 500 assorted resistors dumped across your workbench because someone bumped a plastic drawer tower. Heavy base organizers or wall-mounted bins prevent this. Sort by value and label clearly. It's a time saver and a safety measure when you're mid-project and need the right component immediately. Keep a chemical inventory log with purchase dates and expiration tracking. Some reagents degrade over time. Hydrogen peroxide loses potency, acids concentrate as water evaporates. A simple spreadsheet or notebook tracks what you have, when you bought it, and when to dispose of it. Also helps you realize you've been storing a bottle of clear liquid for 3 years. Get rid of it. Let's move into emergency preparedness and protocols. You're teaching your kids to manipulate electricity, heat, and chemistry. That's the point. But home STEM lab safety includes preparing for the moment something goes sideways, because eventually it will. Mount an ABC rated fire extinguisher within 10 feet of your primary workbench. Press A is for wood and paper, B for flammable liquids, C for electrical. You need all three. A 5-pound extinguisher runs around $30 to $50 and handles most small lab fires. Mount it visibly, train everyone on pass, pull, aim, squeeze, sweep, and check the pressure gauge annually. Stock a first aid kit for burns, cuts, and chemical exposure. Beyond standard adhesive bandages, you need burn gel, sterile saline for eye irrigation, nitrile gloves, and tweezers for splinters or debris. If you're doing chemistry, add a bottle of pH-neutral eye wash solution. Store it in a clearly marked wall-mounted case, not buried in a drawer. For chemistry work, have an eye wash station or portable solution. Bench-mounted eye wash stations run $100 to $300 and might be overkill unless you're running a full chemistry curriculum, but portable eye wash bottles, $10 to $20 for 16 ounces, are not. If your teenager gets a splash of dilute acid in their eye, those first 15 seconds matter. Water works in a pinch. Buffered saline is better. Post emergency contact numbers and lab-specific safety rules. Laminate a sheet with poison control. That's 1-800-222-12222, your local emergency number, and any relevant product hotlines, like the number on your 3D printer filament's safety data sheet. Include lab rules, no food or drink, goggles required for soldering, never operate equipment alone. Post it at eye level. Maintain clear floor egress paths with no trip hazards. In an emergency, you don't want to hurdle a power supply or trip over a filament spool on your way to the door. Keep a 3-foot wide clear path from every workstation to the exit. Use cable management raceways, not loose cords across walkways. Get safety goggles with side shields for every lab user. Cheap safety glasses fog, scratch, and get abandoned in a drawer. Spend around $15 to $25 per pair for ANSI Z87.1 rated goggles with anti-fog coating and adjustable straps. Make them non-negotiable for 3D printer bed leveling, heated nozzles at eye level, soldering, and any work with spring-loaded components or rotating tools.
Run emergency procedure walkthroughs every 6 months. Actually practice. Simulate a small fire. The filament caught. What do you do? Unplug the printer, use the extinguisher, evacuate if it spreads. Simulate a chemical spill. You knocked over the isopropyl. What's first? Ventilate, avoid flames, clean with absorbent pads, dispose properly. Rehearsal converts panic into process. Now, organization and workflow safety. How you arrange the space determines how safe it is under real-world conditions, tired kids, simultaneous projects, the chaos of creative momentum. Home STEM lab safety includes designing for human behavior, not ideal behavior. Separate hot and cold work zones with at least 4 feet of clearance. Soldering irons, 3D printers, heat guns, anything that gets hot should be physically separated from PLA filament spools, paper project plans, and cardboard prototyping materials. A dropped soldering iron rolling across a desk shouldn't land on a pile of documentation. Use anti-fatigue mats in standing work areas. Standing for hours while assembling a robot or monitoring a long print leads to fatigue, which leads to mistakes. A simple foam mat, 20 to 40 bucks, reduces leg strain and keeps focus sharp. Safer, more comfortable work means better outcomes. Try tool shadowing or silhouette boards for frequently used equipment. Outline tools on pegboard with a marker or paint. It's immediately obvious when something's missing. Was the wire stripper left near the 3D printer? And it enforces a return after use habit, reduces clutter and the chance of stepping on a rogue utility knife. Use project bins with lids for work-in-progress containment. Open projects sprawl. Stackable bins with lids isolate each project. Arduino circuit in one, solar panel assembly in another, prevents cross-contamination like metal shavings in the 3D printer filament and limits the scope of a spill. For sensitive electronics work, use anti-static mats and wrist straps. A static discharge won't hurt your kid, but it'll kill a $40 Arduino Mega or a $200 Raspberry Pi. An anti-static mat runs around $15 to $30, and a grounding strap is about $5 to $10. Cheap insurance if you're working with bare PCBs or ICs. Our Arduino Robotics Kit guide covers platforms worth protecting.
Control moisture in basements and garages. Humidity above 60% degrades filament, rusts metal components, and encourages mold on cardboard storage. A dehumidifier, $150 to $250 for a 50-pint capacity, keeps the space safe for electronics and materials. Monitor with a hygrometer, around 10 to 15 bucks. Here's a final check to run before each major project session. It takes 2 minutes and catches about 90% of preventable hazards. Make sure all high-draw equipment is on dedicated circuits or surge protectors. Confirm your ventilation system is operational, fan on, window open, air purifier running. Check that flammable materials are stored in metal cabinets, away from heat sources. Verify your fire extinguisher is accessible and the pressure gauge is in the green zone. Confirm safety goggles and first aid kit are within arm's reach. Make sure there's a clear egress path to the exit. Brief all users on emergency shutoff locations. No food or open drinks in the work area. And if batteries are charging, supervise them. Don't leave them overnight. Let's hit some frequently asked questions. What are the minimum home STEM lab safety requirements for 3D printing with kids? At minimum, you need active ventilation, either a HEPA air purifier or exhaust to outdoors, a stable surface that won't tip if bumped, a dedicated surge-protected power circuit, and mandatory safety goggles during printer operation, especially when leveling the bed or clearing jams near the hot end. Store filament in airtight containers with desiccant. Keep the printer at least 3 feet from flammable materials, and never leave heated equipment unattended with children under 10 in the room. For a detailed setup, check out our 3D printing station checklist. Do I need special electrical work to meet home STEM lab safety requirements?
Most homes can support basic stem work on existing 15-amp circuits if you limit simultaneous high-draw equipment, but if you plan to run FDM 3D printers, laser cutters, or bench power supplies regularly, a dedicated 20-amp circuit prevents nuisance breaker trips and fire risk from sustained high loads. GFCI outlets are essential near any water-based experiments, chemistry, hydroponics, aquaponics. Consult a licensed electrician to assess your panel capacity and install additional circuits safely. How much ventilation is required for safe soldering and electronics work at home? For occasional soldering, under 2 hours per week, a benchtop fume extractor with activated carbon filters positioned 6 to 8 inches from the work surface captures most flux smoke. For daily or intensive soldering, add whole room ventilation, achieving 4 to 6 air changes per hour. Calculate by dividing room volume in cubic feet by 60 to find the required CFM rating for your exhaust fan or air purifier. Lead-free solder still releases irritants. Pregnant individuals and children under 8 should work in exceptionally well-ventilated spaces or outdoors. Here's the thing. Safety infrastructure isn't the flashy part of STEM learning. Nobody writes glowing reviews about their GFCI outlet or fire extinguisher. But it's the difference between sustainable, scaling experimentation and a single incident that shuts down curiosity for good. When your teenager confidently powers up a multi-board Arduino project because they know the circuit can handle it, when they instinctively reach for goggles before approaching the 3D printer, when they store LiPo batteries in the fire-safe container without being asked, that's when you know the space is doing more than housing equipment. It's teaching responsibility as a prerequisite to capability. Build the foundation right, and the projects your kids dream up won't be constrained by safety fears. They'll be amplified by confidence in the space itself. For next steps, review our complete home STEM lab setup guide to integrate these safety protocols into your larger infrastructure plan. Then explore how to organize progressive skill development once the space is secure.
That's it for this episode of the STEM Lab podcast. Thanks for listening all the way through. We've got new episodes coming out every Monday, Wednesday, and Friday, so there's always something new in the pipeline. If you found this helpful, I'd really appreciate it if you could leave a 5-star rating and a quick review. It's one of the biggest ways other people actually discover the show, and it makes a real difference. And if you haven't already, hit subscribe or follow so you get notified the second a new episode drops. See you next time.